First of all, thank you to the FFB for inviting me to present. Again, my name is Ahmad Mohsseni. I'm the Chief Technology Officer for UKBIC. UKBIC is the abbreviation for UK Battery Industrialization Center. And today I will talk about battery production research and how UKBIC fits into this. The presentation is split in three parts. I will start with current state. This is basically an introduction to UKBIC. What are we doing? How our infrastructure looks like, what's our purpose. Based on that, I will talk about the future state of UKBIC, because we are established since 2018. We officially opened last year. We started being operational, but I would like to show you what we intend to do in the next few years and what the main drivers are behind that. And then third part, last part, a bit unrelated, but I brought two use cases so you get a bit of feeling what are we really doing day to day. Current state, I think to start with, it makes sense to understand how UKBIC fits into the wider ecosystem within the UK research and development. On top of everything there's UKRI, UK Research and Innovation, and within UKRI there's a virtual organization called the Faraday Battery Challenge. And the mandate of the Faraday Battery Challenge is to basically support and help out building a battery industry in the UK. And they're basically coordinating three major pillars. The first pillar is the so-called Faraday Battery Institution. The Faraday Battery Institution's remit is really to look into scientific research, looking into new materials, novel electrolytes, beyond lithium-ion, sodium-ion, lithium-sulfur, solid state, and so on. Then the middle pillar, the collaborative R&D, is usually the commercial entity partners up with universities or research technology organizations to push mid-TRL technologies and develop them and make them ready for market application. And then the third pillar, which is UKBIC, which is us, our remit is then really to help scale these products and find the needed manufacturing technologies to bring these technologies to mass manufacturing. And then there's the fourth entity attached to all of that. That's the APC, the Advanced Propulsion Center, which then really looks on the market side and helps companies to establish gigafactories or other battery-related industry activities on the market side. That's how all it fits. So it goes from research to really industrialization and bringing things to market, and how everything is connected like that. And then how we describe this, where we really fit and how it looks, because we are usually distinguish between four different parts. We always say there's the CREM scale. This is really at university level, research level, where you build coin cells, you look into the fundamentals at materials, half single layer pouch cells to understand the mechanisms and fundamentals of battery technology. Then we say there's something called kilogram scale, where you have some specialized university like the Warwick manufacturing group, or in Germany you have the Münster, who have a bit more specialized equipment to build and bring materials into proper cells and pouch cells, or in 2170 or bigger cylindrical cells, to look if these cells and if these materials still are valid in bigger cell formats, and to do the bit of development there. And then there is the ton scale, where we say UKBIC scope is there, because we usually assume that the material and the cell design has a certain level of maturity. So you come to UKBIC, where we then really look into manufacturing readiness, manufacturing technology, and how to get to decent reproducibility, repeatability, and quality standards for cell manufacturing. And then at the end, it gets transferred to gigascale. And before we've existed, there was always this perception that you can go from gram and kilogram scale to gigascale, but that's not the case. You need some intermediate facility infrastructure which can help you to transfer very good technology through manufacturing R&D to gigascale. And then some few key facts to get a bit of feeling what we do. We are 20,000 square meter manufacturing research facility. Our scope is battery electrodes, battery cells. We do module and pack, and all at industrial grade. For us, it's important to do material cell manufacturing, but it should end up all at industrial grades and should be commercial relevant. We call ourselves a learning factory. That's all about. It's important to get all the learning, and all activities we do is important for our partners and customers, that they get the learning so they get enough knowledge and technology readiness for their products to bring to market. So we're looking to new manufacturing processes. We're looking to help them to understand new materials behavior in an industrial environment, new cell formats, new model and pack structures, and so on. And one of the main purpose where we come into play is to reduce commercial risk, because battery cell manufacturing is usually high capex investment, and it takes usually 3, 4, 5 years to set up a facility like that. And with our given infrastructure, basically companies, partners have already something they can use to de-risk their own activities. We are here to help UK industry. We're here to Europe industry, general industry. We are not only exclusively working with UK companies. We're generally working globally with companies. We're an open access facility. One of our primary bits is we don't want to own IP. We have some background IP. We are open to that. We give it to our partners and customers to have a good starting point sometimes. And all foreground IP usually sits with our partners and customers. That's the status as it is today. And then the last bit, very important, it's about delivering skills and training to support the entire battery industry, starting from the intellectual part with skilling scientists, engineers, to process specialists, technicians, and operators. It's a spectrum, all you need to basically build a capable battery industry. There's only a quick overview, what we do and where it starts and where it ends. We really start from mixing, so the electrocoating, drying, calendering. We have the cell assembly capability, slitting, assembly, formation, aging, testing, and then we have module and pack capability. I will not go into much detail here, as most people have an understanding of this. But a bit of look into our facility and how it's structured. We have 2 electrode lines. We have 1 dedicated anode line from mixing to slitting. I think it's worth to mention that at a certain scale of that, it is a basically 200 liters slurry mixer. It can basically manufacture in an ideal state 1,000 liters of slurries per hour. We have a coater with a dry of 40 meters length. The fall width we use can be between 300 and 700 millimeters. Coating and drying speed up to 50 meters per minute, continuous coating. Calendar and slitting, same fall width of up to 700 millimeters, and coating speeds up to 40 to 50 meters per minute. And then the same, we have a dedicated cathode line in place. We have 2 dedicated cell formats. We have a pouch cell assembly. It's a 300 by 100 counter-sided tap, and we have a cylindrical cell assembly line 21700 format, which then we can use to bring in different material component to manufacture different cell designs. And then formation, aging, and testing, highly automated to finalize and finish cells. And then we have a bit of agile, we call it agile module and pack assembly line. It is basically a very manual line to manufacture different variants of module and packs to test them out. And then very important, we have this lab where we do we use it for in terms of cell manufacturing to do forensics, analytics, finding failure modes, confirm manufacturing process, and so on. A lot of expansion area purposely. There's a bit of half the facility still open to put equipment in, and other years we purposely deliberately left this open to do future activities. And what we do in generally, we've categorized basically different use cases. We call it make to print to enable investment. So we are not a facility who's doing contract manufacturing for long periods of time. But what we do is we help companies while they're building their own facility as an interim to manufacture electrode and cells to start, kicked off and delivered to market. We're doing prototyping at scale, what we call. It's really to look into how different materials behave and how can I increase for certain cell designs the speed of manufacturing, how do I get reliability, how do I get good quality standards, and how do I can progress this slowly up to full maturity. Knowledge and transfer, skill transfer is a bit about training to train people and understand how to manufacture cells, what is important, the correlation between material design and manufacturing. collaborative R&D, so looking more into future technologies, future designs, future materials, and then we do a bit of consultancy advisory because market asked us. Some people want to learn from us how we did things in our experience and to transfer that while they're building their own facilities, gigafactories or other battery-related facilities. And then on the market side, we are not exclusively for automotive. We call it general propulsion. So all industries like automotive, aerospace, aviation, marine, which are propulsion, we work with, looking into energy storage, industrial and other applications, which is usually warehousing, robotics, drones. Mainly we work with battery cell manufacturers. And the second strongest customer base, partner base, is usually the battery materials and components value chain. So this was a bit of so far about where we are today, what we do today, and I think it's now worth to talk about what we intend to do in the future. And if we go back in time, UKBIC was initially built on the hypothesis that there's a good UK research and development infrastructure for early TRL in UK and Europe general, but there's something in the later TRL missing, which helps to bring these technologies to market. And when we think about what to do in the future, as a standpoint from today, we have much better understanding what market needed, because since we're operational, we've talked to so many companies. In fact, we talk now about 300 companies or more globally who are already operate in the battery industry or want to enter battery industry, which gives you a good idea where market is going, gives you a good idea where the commercial roadmaps are going. We have substantially better understanding of battery manufacturing complexity. I mean, it's well accepted that you can take your time 5 to 7 years to develop material and chemistries, but then there's somehow a perception that when it comes to manufacturing, you can scale up within 3 to 6 months. And it needs to be appreciated at the same time you develop materials and chemistries, the same time it might take for you to develop the manufacturing process behind that. So it gives you a good understanding now when we do things and when we see things, when we talk to partners, that what their technology is, what capabilities are needed actually to implement these technologies, because it's not always copy and paste to what you have today. Sometimes you have to develop new manufacturing processes. And then the third bit we build up on is we've basically launched last year our operational bit. We've kicked off our commercial project. We kicked off our collaborative R&D project, and we have now a lot of hands-on experience what industry really needs and what they are actually asking for, because sometimes there's the gap between what they say and what they really need. And now being operational and seeing it day to day helps really to understand how our business model and operating model needs to be to accommodate to all these needs. So all these three things, the market and commercial roadmap, the technology and capability roadmap, and the business and operating roadmap, these three things needs really to go into something if you want to build up a future infrastructure program and to do some next wave on the investment to deliver something which is technically relevant, but also commercially needed. So going back to the technology roadmap bit, what you have is when it comes to the technology roadmap, and if you do a bit of Google and all the other things, you always find there are material roadmaps. People talk about the development of cathode and anode materials, electrolytes, but that's not sufficient when it comes to technology roadmap. Technology roadmap should consider the material roadmap, the format design roadmap, basically where's cylindrical going, where's prismatic going, where's pouches going, is there a new cell format coming up, and then there's the manufacturing roadmap, and all three of that, the sum of them make the technology roadmap. And that needs then to be connected to a commercial roadmap. And initially we started with looking into automotive, but where everything is going, and you've heard that from Jens, there will be multiple sectors moving into battery industry, and battery industry is more than only automotive. It is variety of industries involving, and that basically all that input gives us input to decide what we do next. And one of the major decisions we've made is with something we call in-house cell. We've developed our own cell to commission the facility. We've built up everything you need as a cell designer to understand how to design and manufacture cells at industrial rate. We are looking into next generation of batteries beyond lithium-ion, as mentioned. So solid state, for example, relevant or not, and if yes, how does it look and how can this evolve? and then looking into new manufacturing processes at the same time. So I'll give you only a bit of hint and idea. We are currently in conceptual phase how to do. We definitely will extend our lab. We'll probably think currently to have 3 or 4 times the footprint to become better in analytics, forensics, because the best learning you usually get is when failed cells during manufacturing, because that amplifies really the learning. And what we've seen is a lot of methods today are not really developed to give you a very fast route to understand why cells have failed. We're looking into solid state production, and we have discussions how can this really evolve in a very organically reasonable way. We're looking into another cell format, potentially prismatic. We're looking into something we call industrialization room, where we basically have a very empty, clean and dry room where we can quickly bring in technology technology into test quickly, without always saying, oh, we don't have space, oh, we first need to build a clean and dry room. It is ready, and you can basically bring in technology immediately. And then we are looking into a lower scale or 2 lower scale electrolytes, which gives you a bit different, more flexibility of what you can today. Today, with big lines for scale, for high volume, you can do a lot of things there, but it's not always cost for value. And with a more flexible, lower scale line, you can try more things cheaper, more reasonable, in a more reasonable way. And then what's important, this is basically the evolvement of what I've showed before about the gram, kilogram, and ton scale, giga scale. And this is a bit of involvement. This we've done together with the Warwick manufacturing group, but it's not bilateral in that sense. Basically, this is an approach which generally we, as research organizations, technology organizations, they need to work together, to work in a network, because there's different disciplinaries which needs to work together. And how we try to explain things is now and have a bit more granularity is to have to distinguish between the material TRL, which might sit better in material labs and research labs with smaller scale equipment. You have then a cell development TRL curve, which then you need specialized equipment, scale 10 to 50 liters equipment to manufacture electrodes and cells, to lower volume, but with better manufacturing quality. Then you start going to the manufacturing TRL, and then you should have something in place where you have high manufacturing quality, but you need a decent volume to start looking into industrializing these technologies, which we now call flexible industrialization line. And our current line, we will probably rename to volume industrialization line, because that's more about how do I get things then properly manufacturing process developed and to demonstrate that it works against speed and rate. We're trying to work on a much more integrated horizontal vertical integration approach. That's it so far. 2 use cases. Only to give you an idea, I've brought something which is commercially not sensitive. What we've started working a time ago is life cycle assessment, because what we've identified is when you look at public available data so far, or a year ago, there was not good public data about what is the carbon dioxide footprint of battery manufacturing facility. What is the reality? You could find everything between 10 and 300 kilowatt hours of energy consumed versus energy produced. And from a European perspective, when we say core cell sustainability is at the core of cell manufacturing, we need to start understanding what's behind this end-to-end, from the supply chain to the recycling bit. And we need to really understand in every bit of value chain, especially in our case in cell manufacturing, what is the data, how can I get the data, and how can it help me then to kick off other projects to get more sustainable. And what we've done is we've kicked that off. We work together with FFP, for example, on a bit of knowledge transfer and challenging the methodology we've done. We've really measured real data in our facility when we manufactured, because we have industrial representative equipment. So it's primary data we could use. Other studies before a year ago, they've only used secondary data or some estimations based on very low scale lab lines, lack of transparency. And then we've created, for example, a white paper that triggered a lot of other discussions, because now we're talking to a potential gigafactory builder who's challenging his own process again and thinks about how can I become better, more sustainable, what are white spots I've not seen before. It was leveraged by a recycling company who challenged their supply chain to understand where are their white spots. So it was not really asked by market in the first place, but once you have it and you disseminate, you will see that people react to it. And that's, I think, the power of doing battery research in Europe, because you have to start somewhere, you've created something, and then you will see that market and your partners around are reacting and really grabbing it. I think there's not always market pull, there's also a technology push approach sometimes you have to pursue. A different use case that's quite odd, that's when we've commissioned. The challenge was when we've really commissioned, we couldn't calendar. And we couldn't calendar, it was so drastically because we had web breaks and we couldn't commission the equipment, which gave us great learning, because you see things like we've seen embossing and corrugation, and you can't build cells when your electrode looks like that. Even if it's if you improve this, it's not sufficient. So what we've did, and that's, I think, really important from a research and development part, cell manufacturing is not only practical. Sometimes you have to stop the practical part and go to method building, into the intellectual part of cell engineering back, and understand then the relationships between material, the design, and the manufacturing process, because they're correlating, and it's quite complex correlation, and it's not always clean. You cannot always see it with your eyes, so you have to sit down, build an intellectual model behind that, which gave us a bit of framework how things are working. I've done a design for experiment study, quite comprehensive. We found good knowledge about our equipment and operational window, and that intellectual knowledge basically gave us then the idea how to overcome all these issues. Today we don't have massive issues in electrode manufacturing anymore. We've overcome them, and we've understood how to overcome them. And it's not only manufacturing related issues. What we see today is that was for certain material composition, for certain level of foil. And the real answer is, how can I basically get to an equation, no matter what material I get in, no matter what kind of foil I do get in, what is the right approach and what is the modeling equation to solve it right away? Because the benefits of that goes straight to industry, and it helps them to skip over this issue, because what you don't want to is you want to face same issues all over again. You want to solve them, you want to fundamentally solve them, and then get going. So our partners benefit from them because we've solved that and we transfer that knowledge to them. It helps you to engage with technology suppliers, because one of the things what we're seeing is there's a lot of technology around, but as long as you don't identify the real problems, you don't know that you need them. So you will see that a lot of technology suppliers around might not have ever thought about battery industry, but might have key technologies which will enable battery technologies. And then it gives you a good idea where research and development needs to focus to build up capabilities for a strong and successful European cell manufacturing business. That's it. Thank you very much.
Thank you, Ahmad, for your quite interesting talk and the, let's say, deep insights about what UKBIC is doing and what challenges were you facing during your ramp up. Are there any questions out of the audience? Not yet, but to be honest, I have one question. And during your talk, you mentioned that there was the opportunity that going from the kg scale to the giga scale in, let's say, one step without covering this ton scale is possible. And obviously it is not possible, and you are for the, let's say, ton scale there. Can you name some challenges when you move from this kg scale to the giga scale, what you were facing?
Interestingly, several challenges. What we see is quite a sensitivity behind changing small amounts of binder, like 0.25% can have massive impact on manufacturing process. It's one of the recent things we are seeing, and people need to understand how there's always the sensitivity between my material composition and my performance. There's also how is my material composition impacts my manufacturing process. I'm not saying it's impossible to solve. It's a massive challenge, but you have to think end to end. You have to start thinking how everything is connected. And when I change here one thing at the beginning, how does it cascade down along my entire chain to the end?
Thank you. I see. Within the chat, there is another question which is quite close to the one I was asking previously. What is the main challenge for quality in scaling from lab to ton scale?
What you do is usually when you're doing lab, what you have is usually few good, well experienced people who it's handcrafted a bit, and they have a quite good understanding what is good, and they can see it with their eyes, and it's good enough for what they're doing. If you go and try to scale up, you're on a different level. Your eyes can't measure in 1, 2, 3 micrometers. Your eyes cannot, along the manufacturing process, find all inspection spots. So inspection becomes more important, quality becomes more important. But if you just say quality is important, you start to say I measure everything, you will end up manufacturing nothing. Because I remember when we started manufacturing, we had a very long control plan, and then you spend so much time measuring that you're not manufacturing. I think the sweet spot will be quality is of utmost importance, but you have to come up with some kind of intellectual approach to understand what is important, what makes a change in manufacturing, and what inspection technology do I need to implement to get better results.
Okay, thank you very much. Thank you for your presentation.